last spring in 2020. So just a little less than a year ago, I was going to school there as well. And I did focus mainly in my senior year working with FPGAs. I did my senior design project with it, and I took classes that maybe some of you have taken or heard of with Professor Mirzai and maybe Professor Mailer. Um, Recently, I got hired into Raytheon Technologies just about 4 months ago. Today, actually, was my hire date. And I am now living out in Tucson, Arizona as an FPGA and VHDL engineer out here. So just so you know a little bit about my background, also at CSUN, I did used to be a tutor for the Academic Enrichment Center. So I do enjoy teaching. So hence why I'm here with this event. I'd like to inform you all a little bit about the work that I do that I've learned in my studies at CSUN, as well as what I've learned so far in the professional work environment. However, I do want to make this event as casual as possible. So, I may go through this PowerPoint, and if anyone has a question or just wants to chime in with something to say, feel free to just unmute your mic and interrupt me. Maybe I'll get to your question just after I finish my thought, because this will be a lot of info coming at you. I'm trying to keep it a little bit basic because this is for beginners, but there's a lot of maybe new topics that not everyone knows about. So once again, if you have any questions, just feel free to unmute your mic and interrupt me. So we will go ahead and start off here, and we will start from the basics of what is an FPGA. So an FPGA is an acronym that stands for the Field Programmable Gate Array. That's already a mouthful in itself, but essentially what it is it is programmable hardware. Basically the difference in this board down here in the lower left from, say, something that you may have heard of like an Arduino or a Raspberry Pi is that this is actual hardware that we can configure, whereas the other two are going to be focused on software. So an Arduino, if any of you have ever played around with those, is a microcontroller. It's good for basically taking sensor data and doing small calculations. A Raspberry Pi would be the next step, which is a microprocessor. That one you can actually run full-on software like Linux on. And then FPGA is kind of a specialty. So this one, like I said, is programmable, but you can program hardware circuits. Think if you have taken it ECE 320, digital circuits, you can program actual logical functions, which is an advantage over the other two because hardware is much faster than anything in software, anything that can do. But I'll get a little bit more into that later. So essentially that chip on the bottom left that I circled, that is the FPGA chip. That's where the programmable hardware lives. And around that picture is all of the peripherals that we can interface with that FPGA. Just like a microcontroller, we can take signals from the outside world, like a switch or a light, an LED, and we can control those. So these FPGAs, however, take some special programming, unlike an Arduino or a Raspberry Pi. They take something called a hardware description language, which is an HDL, rather than a software language, which is C or Java or Python, anything that you may have done software-wise. In the land of hardware, everything's different, unfortunately, and it takes a special language to be able to code up that hardware. In hardware, you have things to deal with such as clocks and logical functions and timing, and unfortunately, software languages such as C and Java can't describe that for us. We can't synthesize that. So these two main languages called VHDL and Verilog were made just for this purpose. VHDL is actually an acronym in itself. I always forget the V because it's funny. The V is actually an acronym in itself. It's like very high level hardware description language. It's kind of interesting. And Verilog is the other language. So a little bit what I touched up on here is the difference between hardware and software. So a lot of you may be familiar with software so far. That seems to be a lot more popular. And essentially, software runs on a pre-made hardware processor, which is usually something called an ASIC, application-specific integrated circuit, which I'll get into that a little bit later as well. But essentially, the software runs on CPUs. It runs on hardware in our laptops right now. Our Zoom software is working as we speak to give us all of our info right now. So software is great, but it uses prefabricated registers on a processor that's already made. That processor was made, fabricated in a factory, and we're using it now. So essentially, those processors, however, have one caveat in that they have to do things sequentially, and they're generally made for general purposes. They're multi-purpose. They can be used for many things, such as gaming, for cryptocurrency mining, for uh, any sort of software, an internet browser, YouTube, whatever it may be. So the difference, though, is in hardware, we can code up hardware in an HDL and place it on an FPGA or a similar device. And what this does is it implements physical logic inside of that chip. We can actually manipulate the very transistors inside, which gives us an advantage, gives us speed. We can physically design this chip around a specific purpose, which would be much faster than anything software can do. So that is the interesting part about hardware versus software. However, another advantage hardware has is that it's also good for parallel execution, which you may have possibly heard before. Essentially, with software, things are done in sequential execution. It's one thing at a time. It performs one instruction, fetches the next thing, and does that. In hardware, we can code up multiple jobs at once. We can tell it to do multiple things, like that's very useful in digital signal processing. Think cleaning up an image in real time, filtering a video in real time, anything like that. We can do that a lot faster in hardware with dedicated hardware. And like I said before, I just want to put this note out there. If anyone has any questions, feel free to just unmute your mic and interrupt me. But I'll go on if no one has any questions. So as I mentioned before, coding up hardware. It sounds kind of funny when you think about it, because hardware, we look at a transistor or a circuit or something in one of the labs at CSUN on a breadboard. How do you code that up? It doesn't sound right. However, like I said earlier, hardware is coded with special coding languages, which are called HDLs. So I mentioned before a little bit, but these contain special constructs that we don't have available to us in software language. So we're able to describe what these circuits that we make in ECE 320, what these circuits do in a software language. So it's a very powerful tool, but unfortunately, it's got quite the learning curve to it. Everyone kind of learns software usually in engineering at some point, but these HDLs, you kind of have to flip your mindset and think hardware. Everything's in tune with a clock or combinational, unlike software. So we'll touch on that in a little bit, but as I mentioned before, the two most popular hardware description languages are Verilog and Vhdl. So specifically at my job, we code FPGAs and other devices that are similar, and we 99% of the time will use Vhdl. It just tends to be in the industry a standard for FPGAs, anything with configurable logic, it's usually called. Whereas Verilog is typically used for application-specific integrated circuits, which is that mouthful right there that comes down to be an ASIC. So ASICs are typically going to be your computer processors, things that are made on a single chip, and they're hard-coded ones. You can't reprogram them. There is a lot more behind-the-scenes action, I guess, that you would have to think about in ASICs as far as the physics of the device. Verilog typically has more constructs and behind-the-scenes tools to help with that sort of engineering. However, as I said in this bullet point, either one can be used for FPGAs or ASICs. It just tends to be that industry likes to prefer one language over the other depending on what is being programmed. And beyond these two languages, there is some experimental techniques coming out nowadays. If you do take ECE 520 with Dr. Mirzai, he will go over some of this. There is a version of C now, C, the regular software language, that can actually synthesize into hardware designs for an FPGA. It's still quite experimental. There's not many people in industry that are using it right now, but if this language does catch on in the future, it could bring a lot of new industries and technologies into FPGAs and ASICs. So yeah, it's kind of an exciting and up and coming topic. Even as I've been studying it, I've seen FPGAs more and more everywhere in projects, even little individual projects where people would normally use Raspberry Pis or Arduinos to do something. I'm now seeing people use FPGAs, which is kind of cool. So if you do want to get into FPGAs, you could be kind of preparing yourself for something in the future that might be pretty big. So yeah. On the next page here, we'll have a really quick example of what VHDL looks like compared to software language. So you'll see on the left here, for those of you that have taken ECE 320, that's what a regular digital circuit would look like. We describe it with logical gates, ands and ors. So in this case, we have two AND gates on the left and an OR gate on the right. So what you would see on the right is that we created three statements that would describe this circuit in an HDL. You'll notice on the left picture again that each wire has a signal name. We have our inputs on the left, A, B, C, and D, and we're going to have our outputs on the right, which is the Y. And we have some intermediate signals kind of connecting the two gates, which is Y1 and Y2. So you'll notice on the right, there is an architecture. And we see architecture test of example is, and then a begin, and you're going to have these three statements. So essentially, if we match up this code to the picture, you'll see the first statement, which is Y, and you'll see the character right there is actually an arrow pointing left. It's not a less than or equal to or a greater than or equal to sign. Essentially what we're saying is Y gets Y1 or Y2. So you'll see right here, that's what this equation is describing. Y, the output, gets Y1 or Y2, because this is an OR gate. And just like any other software language, we put a semicolon at the end, and we describe the other two gates, which is Y2, this output, gets C and D, and respectively Y1 gets A and B. So this is what we would call structural coding in VHDL. We're actually looking at the logic equations of the circuit on our left. Eventually, once you get deeper into VHDL and FPGAs, you're going to learn more about behavioral coding. I think I might have an example in a little bit later in this presentation on that. But just to ease you guys into it, I wanted to give a simple circuit and some structural coding. Behavioral is typically what you're going to use in the industry. It's a lot more powerful, but you got to start somewhere, so start with the basics. So next, I also just did want to touch up a little bit on the differences between these two technologies. I've already mentioned them a little bit, which is the FPGA, Field Programmable Gate Array, and the ASIC, the Application Specific Integrated Circuit. So as I said before with an example, ASIC is typically going to be things like your computer processors or your graphics cards or something that even goes into devices like a coffee maker or anything, a microwave. They're in almost everything. Typically, those devices take a lot more engineering time to make sure they're ready for the market. Um, once these things are fabricated, they're coded up once and they're fabricated in a factory. You can't really go back and change your design without spending a lot of money. So there's usually a slow time to market because engineering is very thorough with ASICs. Whereas with FPGAs, they're reprogrammable. They're programmable in the field. That's where the name comes from. So because of that, we can code up a design, upload it just like we would any microcontroller or anything when we start a program, and we can test it. And if it doesn't work, we just go back to the drawing board or change it up a little bit and re-upload it and test it again. So that's one of the advantages that FPGAs has. Now, the second cost though would be NRE, which if you're not familiar, that would be non-recurring engineering costs. So this is something like paying your engineers to develop this technology or to develop the circuit. As I said before, ASICs take a lot of engineering willpower to make sure that they're done right. So even though the chips themselves are cheap to make, all that cost comes from the design and the verification of those. However, with FPGAs, that's not a very high cost because once again, they're reprogrammable. So if somebody screws up a circuit really fast, then they can take 10 minutes to change it up and just re-upload it again. There's not as much verification needed. The design flow, that kind of goes again into, there's a lot more verification needed to be done for ASICs with physics and whatnot. With the FPGA, it's a lot more simple since there's not as much riding on will this product work right out of the gate versus, oh, I can just try again. The unit cost, as I said, ASICs are very cheap to produce, high engineering cost though. FPGAs are the exact opposite. FPGAs, there's not a lot of engineering costs since there's not as much riding on it. You can reprogram it. However, the actual chips do cost significantly more than an ASIC. So that's kind of the trade-off that you get. ASICs, a long time to market, but very cheap once you get it right. Whereas FPGAs, you're going to be paying a higher price tag up front, but you get a lot more design capabilities and a lot more leeway to get what you want done. Performance, ASICs are typically higher performance because of all of that engineering costs during the design phase. You can squeeze every little bit of power that you have to get as much performance as you need. FPGAs are prefabricated devices. So it's an interesting concept just because FPGAs are fabricated similarly how an ASIC is. They're made in a factory. However, there's a different sort of technology in that they're prefabricated but can be reprogrammed. So essentially, you don't get as much out of the device because that reprogrammability comes at a cost. You won't be able to get the screaming fast performance of an ASIC, but you do get the malleability of it. Power consumption, ASICs are typically low, whereas FPGAs are a lot higher. Once again, that comes into the design. The design of an ASIC, so much goes into it. You get very low power, very high performance. FPGA, you get a lot of power for okay performance, depending on how you verify your design. And the unit size, it says FPGAs are medium and ASICs are low, but they're typically around the same size. I mean, we're talking millimeters here, so it's not going to be that big of a difference. But I just wanted to touch up on that because FPGAs and ASICs are very similar. So if any of you were looking to do anything in the industry with FPGAs, I would also look at ASICs as well. It's the same design process, just the verification is a bit different between the two. So if you like coding hardware or like the idea of it, either of these are very booming industries and they're very similar. I wouldn't mind going into ASICs one day just to try it. So just wanted to touch up again, sequential circuits can also be synthesized in an FPGA. The example that we saw before, just a couple slides ago, I'll go back to it. This was a combinational logic example. There was no clock involved. So I just wanted to point out that in FPGAs, obviously you can have sequential circuits involving a clock. So you have your flip-flops, your registers, your memories, you can make state machines, and it can get as complicated as you can make an entire CPU if you really wanted to. It's kind of hard to do as an individual rather than a whole team, but it is possible. In fact, some people, some of these companies that have made FPGAs like Xilinx have actually had their engineers code up CPUs for their devices, and you can actually use their code and upload it to your FPGA and get basically what they would call is a soft core CPU. So you can run software on it. They do call it a soft core CPU just for the fact that it gets programmed onto the chip. This is the opposite of what a hardcore CPU would be called. A hardcore CPU is the physical ASIC device. That's the one that's running in your computer. It was fabricated and it will never be reprogrammed again. A softcore CPU is a CPU that can be uploaded to a chip. So that's this FPGA. So it's interesting, just the fact that you can actually just program a device to become a CPU or anything else. So it's kind of a game changer. Just once again, going back to this slide here, your performance would severely be diminished because of that. Hardcore CPUs are always going to be faster than softcore CPUs. But if your design calls for a CPU and you don't happen to have a hardcore CPU in your design, then that might be your route. So I also wanted to touch on recent FPGA examples that I've seen. I did mention that I've been seeing in the news a lot of individual projects. These engineers from home that have been programming cool devices with Raspberry Pis and Arduinos are now moving on to FPGAs. So I've seen some of these in the news. Some people have made basically a Game Boy out of an FPGA, and I think it's coming on the market. And you can actually buy one of these for, I think it's like $100 or something. However, this is way better than anything that has been done with a Raspberry Pi. Those devices emulate a Game Boy in software, whereas an FPGA, people actually looked up the documentation of a Game Boy, edited it a little bit, and this is essentially the same hardware as a Game Boy, just upscaled. It's got higher resolution, it's got internet connectivity, but it even takes the original Game Boy cartridge in there. Because this is hardware, it works on a 1-to-1 ratio 100%. So FPGAs can do something that software can't for these sorts of projects, is that there's no need to emulate in software a video game console. You can literally just code up one in an FPGA and have it work, just like the old Game Boy 20 years ago. So I thought that was kind of a cool project. It was unique. It changed things up a little bit. Another one that I saw is you can create a cryptocurrency miner out of an FPGA. So if you're into that sort of thing, you can buy an FPGA. People have uploaded their code and you can start mining cryptocurrency and making money even off of that. So that was kind of an interesting topic. And then a lot of previous projects that I've seen in the past few years have been with the real-time video and image processing. That's a very popular one. FPGAs are very good at doing real-time image processing. So that would be another one to look at. And I did put some links here if you guys did want to check them out. I'll make sure these slides are available too. Maybe Jason can send these out after the presentation. But yeah, if you guys are interested in looking at some of these projects for yourself, got some links there, and a website down here that I've seen has hundreds of projects for FPGAs. Really good stuff for individuals, stuff that you don't need an entire workforce to produce. That would be a good thing to check out if you guys are interested. So hardware engineering, something that's been taught to me in the industry as well as at CSUN, is the idea of reusability. Essentially, it's don't reinvent the wheel. You can create hardware at a lower level in an HDL, such as a USB data link. A lot of these boards for FPGAs have a USB port on it. For instance, you can code up in an HDL the USB communications functionality and save that in a general term. And then once you have a upper level design, like let's say you wanted to make an entire processing system on your FPGA, then you just instantiate that piece of code into your upper level. Basically, what you're doing is you're copying and pasting that code that you made for the USB functionality, and you put it in the top level saying, I want a USB port in my computer system. So that is something that will be practiced if you do get into any sort of digital hardware design classes. It's something that's used in the industry as well. It's very hard to start at the top level, any sort of engineering project. You know, the big picture, everything looks so confusing, so daunting. You have to break it up into little chunks that one person can do at a time. You know, have someone code up a memory, have another person code up the USB, have someone code up the arithmetic logic unit of your CPU. And then once these are verified, you can just bring them all together into one system. And that's how a lot of these projects are made. The same goes for anything in the ASIC world. It's not just FPGAs. You know, your Intel or your AMD processor in your laptop. These engineers start small. They can't do the whole system at once. They have to focus on little bits, verify it 100 times over again, make sure it works, and then incorporate it into a bigger system. The next thing I wanted to talk about and how hardware and software is different is that hardware has a lot of verification that it needs to go through. Does someone have a question? Or maybe somebody just accidentally unmuted their mic. Okay. So yeah, hardware is different than software, and it takes a lot more verification to make sure that your circuit that's uploaded to this device works. Software kind of has that advantage in that if your program doesn't work, you just, look at the error code and you change it up. And hardware, you have to worry about a lot more things. Hardware is simulated, synthesized, constrained, and then placed and rooted on the board. So that's a lot of words. I'll kind of go in a list here and kind of specify what each one means, but hardware is simulated. So what that means is that we have to test our circuit and make sure it makes sense logically. So going back to that example that we had a few slides ago on the AND gates and the OR gates. So we have to make sure that that circuit is logically giving us what we want at the output. So we have to run through all the tests, change up all of our inputs, and make sure that 99.99999% of the time, it's going to work. It's logically what we want. So that's what we do through simulation. We test all of our stimulus, we give it stimulus, and we check the output of our circuit and make sure it gives us what we want. However, maybe that would be where software would end. You get what you want and then you move on to the next thing. But with hardware, there's a much longer process than there is in software, because once you simulate it and you have what you want, then you have to put your verified code into a tool called a synthesizer. So what the synthesizer does is it takes your code of all your statements and it's going to basically translate that into something that the tool can use to place on our FPGA. And what that result is called is a netlist. So a netlist is essentially, if I go back to this slide, this slide, it's going to look at all these connections here and make sense of where the inputs and outputs would go, essentially from a logic gate standpoint or even a transistor standpoint. So a netlist is going to be basically just a giant list of all of your nets, they're called, basically your wires. and then it's going to make sense of that to be placed on your device. And even once we get that, we're still not done, because every FPGA is a little bit different. Some have more inputs and outputs than others. Some have more hardware than others on the inside, which I will touch on a little bit later. But that means that that netlist that we got from the last step and the synthesizer, that synthesized netlist has to be constrained for the device that we're using. So in FPGAs, for instance, at my work, for one project, we're using probably 8 different FPGAs that are all from different vendors, different multitudes of everything, hardware, inputs, outputs. So essentially, we have to constrain that netlist for the specific device that we're working on. So what that means is we have to constrain it by saying, I want this pin on my FPGA to be input A, and I want this pin to be output Z, anything like that. Constraining goes for what pins you want to be your inputs and outputs, but also it goes into what's available to be put on the device. FPGAs have a finite amount of resources. So essentially, if you wanted to code up an entire computer system with RAM and CPU and a graphics card in it or something like that, you're only going to get so far. Your FPGA only has so much hardware that can be placed on it. So that has to be constrained as well. Not all the time can your design fit on a certain FPGA, and then that's where you'd have to either go back to your design and try to minimize it in any possible way you can, or get a different FPGA that has more hardware resources available to you. Constraining is still more than just pins and the area of your hardware on your FPGA. It also has to meet timing. Timing is one of the most important things in FPGAs, because if you want your circuit to run super fast, you have to make sure that it still works logically. Essentially, if you've taken certain classes at CSUN, maybe ECE 422, I believe, Digital Electronics 2, we talk a lot about setups and hold times of transistors, and how if those are violated, then our logical circuits don't have the result that we're expecting. So when you have a giant design like this, a lot can go wrong with timing if you don't account for it. So you have to constrain your design for timing as well with FPGAs. Luckily, with FPGAs, because they're prefabricated by these companies like Xilinx and Intel, they know what the delay is between, say, 2 points in their FPGA. So if we're making a design, it can tell us, if we mapped out from point A to point B, how many nanoseconds does it take for our signal to travel across that wire? They would know. However, maybe our design is asking too much of this FPGA and it can't meet that requirement. Then we would have to go back and try to maybe place point A and point B a little closer together, or to even change up our design entirely. So there's a lot that goes into designing an FPGA. The good news is that the tools that have been made for this, though, do this very well. In my experience so far, I haven't really had to deal with timing constraints or area constraints yet in my workplace. Usually the tools do a very good job of this, but for instance, in the ASIC world, timing and area is everything. You aren't limited to a single device. So essentially, you're trying to get this working, get it as small as possible, as least power hungry as possible. So there's a lot that can go on in ASICs, but luckily with FPGAs, everything's prefabricated. The tools do a good job. So that is something that can luckily be kind of swept under the rug a little bit. But that does leave us to our last thing. Once everything has been simulated, synthesized, and constrained, the place and router will try to find a possible way to place your design in the FPGA that meets those constraints. So this is going to physically look down inside of the chip and say, hey, I'm going to place this logic element maybe this AND gate at this X and Y axis of the chip. And I'm going to place the other one, right next to it, or maybe across the whole way to the other side of the chip if timing isn't too big of an issue. So the place and router can do many different place and route routines. Essentially, you can tell the place and router if you want your design to be constrained for area the most. You can tell it what your biggest concern is. If my design takes up 95% of what's available on the FPGA, maybe I want to try to make that as small as possible and maybe fit as much of my design on there as possible. And timing isn't so bad for me. Maybe I don't have to run my clock as fast as I initially thought. Or maybe it's the other way around. Maybe my design is very small, but it needs the best timing possible. It needs to have a 2 gigahertz clock or something like that. Then you would tell the place and router that, and it would try to place everything closer together so the delay between the wires and the gates are much smaller. We have to deal with physics that way. We can't place something on one side of the FPGA chip and one on the other and expect a very small delay. That electric signal has to travel across that whole chip. So there's different ways you can constrain it for depending on what your design is meant to do. I know that was a lot of info, but it will also come up on this slide as just some blocks here. So usually the design flow with any sort of hardware, not just VHDL, is you start with a block diagram. What are you trying to do? What is your circuit? Are you building a CPU? Or are you building a signal processor? You can map that out, figure out what you need, and then you would go to coding. And coding, it takes place in your HDL. It would be in Vhdl or Verilog. And once you've coded it up, you compile it, which basically, just like regular software code, compiles it and makes it available to be simulated or run. And once you simulate it, that's where you verify logically if your design is what you want. And if it's not, that's where you take this arrow back to coding. You go back, recode it, make sure it's doing what you want, and go through the same stages. Once your simulation is verified and the circuit is doing what you want it to do, then you come down here to the backend steps. And this goes into what I was saying with the synthesizer. It synthesizes the circuit right here. It actually creates the netlist and makes sure it can be placed on the device. Sometimes, depending on how you code things, synthesis can fail, and you would have to go back to the coding and make sure that everything is a legal action, as in VHDL. Make sure there's no syntax errors or anything that's not allowed. But if it does pass synthesis, then you would move on to fitting, which is essentially what I was saying in the last slide about constraining. You have to constrain your design or fit it onto the device. You have to constrain it for area if you only have so many resources, or timing if your clock can only run so fast. Then you place and route it, and you check the timing once more. You verify that it works, and this is usually a painful step, just as it says, painful but not uncommon. You place it on your board, but then you realize, with this certain clock speed, maybe even just 5% of the time your circuit may fail, but you can't take that risk. You need the circuit to work 99.999% of the time, because if you have a failure, that would be very bad. So this is where a lot of engineering is done to make sure that your circuit works, but it is not uncommon that it won't work, and you have to go back to either try and fit it again, or if it's so bad, you actually have to go back and redesign it in your code. And that is very painful. So I just wanted to kind of show you guys what actual VHDL code looks like, kind of in a fuller view. This is still going to be, well, this is behavioral code. This is a little more advanced than the first example that we saw. I'm not going to go too into specifics on some of these other statements. Some of these are just needed in every piece of VHDL code because there's libraries that need to be looked up to synthesize. But essentially what you have in VHDL code is an entity that is the piece of hardware that we're trying to describe. So this entity is named 1-bit add. So a bit, in hardware, we're trying to add basically what this is a full adder. If you take an ECE 320, you've dealt with those. So you're trying to add bits together, and we usually have three inputs. We have an A, we have a B, and we have a carry in. Each of these are only 1 bit, and usually on the other side we have a sum and a carry out bit. And we describe those as inputs and outputs here as well. And we say, okay, those are all of our inputs and outputs, all of our ports. So we say, okay, that's the end of our entity. But now we have to describe what we do with those inputs and outputs. And that comes into the architecture. So the architecture is, okay, we've established our ports. We have this black box of what our circuit's supposed to look like as far as our inputs and outputs. But what is the nature of inside of this black box? We have to describe that. And here we do it with behavioral code. We basically create equations to specify what we want in our outputs. We have our two outputs listed here, which is carry out and sum. We specified what those were up here, 1-bit outputs. And we essentially say what a full adder does. This is still kind of structural coding because we use ands and or gates, as you can see here. This is going to be the 320 way of doing it with K-maps, Carnot maps. So we specified what the carryout gets and what the sum gets. So this would not be the smartest way to do it in VHDL. We can make it a lot more efficient and easier in our brains, which was this little piece of code that I put down here. We could have taken all this jumbled up mess and put it into one statement, and that's the beauty of behavioral code, is we can actually make more sense of it like software. If we want to add things, we literally just say A plus B plus C, and that output goes to sum and the carryout. So that would be the way that I would do it now that I've had more experience, but this was just as a simple example. But essentially what we're doing here is we're creating our black box of our inputs and outputs, and then we describe what is going on inside of that black box to give us those outputs. And this would be our VHDL code. We would synthesize this, and then if that became successful, we would simulate it. And for some of you, this may be a familiar window. This is a tool called Vivado that you're going to use a lot within ECE 420, 520. Essentially, this is a tool from Xilinx where we can do all of this stuff. We can compile VHDL and simulate it when we're done, and eventually synthesize, which is down here. But essentially what we're doing is we're taking this entity and we're running it through simulations. So you'll see around the the red box here, we have our inputs A, B, and the carry in. And then just below that, we'll have our sum, SO, S out, and our carry out. So we have our three inputs and our two outputs. And you'll see here we have basically a waveform. What we did is in another file called the test bench, we we stimulated these inputs right here to become certain values. So we're dealing with binary here, so you can only have ones and zeros. So you'll see starting at the 1000 nanosecond time mark, we set our inputs A and B are going to take a 1 signal on. This is an active signal, a logical 1, whereas our carry-in has a 0 value. So we stimulated it. We told it basically to have these values. And then once we set these values, then we look at our two outputs and we verify that it's working correctly. So you'll see here, our sum out is a logical 0 during the same time. And our carry out is a logical 1 on this waveform. So what we do with this info now is we look along this vertical axis here, and we'd see if this would make sense with our circuit. We know in a full adder, when you have A plus B, basically 1 plus 1, that should equal 2. However, we're dealing with binary here, so we can't stick 2 in our sum. 2 becomes our carry out, so that's why carry is now a 1, and our sum is now a 0. And you'll notice as we go along, 1010 nanosecond time mark, notice we changed our stimulus. Our carry-in input went up to 1, and you'll see our outputs down here changed because of that. Notice now we have a 1 on both of our outputs because basically we added 3 together. We added 1 plus 1 plus 1, which would give us 3. In the binary world, that is 1, 1. And that's what these two are doing here. So you'll see as we go along, we try to test all of our all of our inputs to make sure that our outputs are verified and correct. I'm not sure that they did that in this example. This was just something that I grabbed online. It's not even mine, but essentially you'd want to test all of your inputs and make sure that they are giving you the correct output. So that's the sort of things that you do in simulation. You have to test all of your possible results and make sure that your circuit works logically 100% of the time. So typical tools for programming these devices, FPGAs and SoC, which I have not touched on yet, but essentially an SoC is just a system on chip, it's called. It's basically what your phone is made out of. There's actually a bit of specific programmed hardware on there, as well as a software hardcore processor. It's a very popular device now because you can get the best of both worlds. You can get your customized hardware and you can get your fast software processor. But essentially these tools that I listed here can do everything for those. Xilinx Vivado is the one that maybe a lot of you have used at CSUN actually. It's typically used for any sort of up-and-coming beginner interface because it's a GUI, a graphical user interface, and it has all of those tools in one that I specified earlier. It has the coding interface, it has the simulator, it has the synthesizer, it has the constrainer and the place and router. So that one is a very popular one to use at first. Another one is Simplify. These are lesser known ones to a lot of you maybe in school because these are used more in the industry. If you have taken ECE 526, you may have used Simplify. It's typically used in a Linux environment and it's used to synthesize the circuits. So that's what takes your Hdl code and turns it into something the computer can recognize, that Netlist. So that's used even at my work. It seems to be an industry standard. And then we also use Libero is another tool, which actually places it on the FPGA and tries to root it. So not all of these tools actually do all of those functions. Some tools were made specifically to synthesize, while others were made to simulate, or others were made to place and route. So these are an example of those. ModelSim and Questa, that's another program that's used specifically just for simulating some of these designs. That's something, once again, that I use at my work. So you'll see down here in some of the pictures too, you'll see kind of some of the design flow. You don't need to know what an NCD file is, but essentially what I was saying earlier about constraining your pins and your inputs and outputs on your device, you map it to the FPGA and then you look at the results and then you look into verifying timing, which is what I was talking about, that important thing earlier, and you make sure it works and then you go on. Another slide over here goes into how implementation works, which is the place and router. It takes your synthesized netlist, so see how it's an actual representation of your circuit, and then it places it onto these blocks. And then once these blocks are placed, then it tries to route a signal between all of these blocks on something called the switch matrix, which I will get to on our next slide. And that's the architecture of an FPGA. So inside of each one of these chips is a few components that kind of make up all of it. A CFG is a configurable logic block. Essentially, it's all of these blocks. And what they're made up of is various things. The most important would be a lookup table, and that is pictured here. So a lookup table is kind of interesting. This is a 4 input. Essentially, in this whole block, it's able to do almost any logic function, and yet it's made completely out of RAM and multiplexers. It's very interesting because what we take to be maybe an AND gate and an OR gate, what we now do is we store values of ones and zeros in here in the SRAM, and then our inputs become the stimulus to control a multiplexer. And it will take the ones and zero values and basically pass them along to the next level of multiplexers and look at that input and keep going on and on until you get the end, which then you have two paths. If it's a combinational design, it just skips the flip-flop and goes right out. Or there's a flip-flop right there, which would be your memory device. It's just a D flip-flop and it would hold your value. So those are lookup tables and they're held within the configurable logic blocks. And then once those are all placed, the switch matrix is the routing part. And once again, that is what places the wire in between all of these blocks to make up your circuit. And then we do have input output blocks, which those are pretty self-explanatory, but that would be our in and out of the outside world. We take our signals from these pads, our pins on the FPGA. And then this was kind of just a reiteration. Once again, we have our blocks and the switch matrix. This is the reprogrammable part. You know, we load up our design on these blocks and we route using the switch matrix our connections. And you'll kind of see here, this is a black box design of a lookup table. So typically they're used to be adders, subtractors, things like that. Any sort of logical function, ands, ors, nors, any of those. And they do usually contain a flip-flop as well. So within FPGAs, there are also special configurable logic blocks, I guess you could say. This is kind of their counterparts. FPGAs are typically favored for a lot of operations, like I was saying earlier. Instead of a microprocessor like a Raspberry Pi performing signal processing, you can do it much faster on hardware, such as an FPGA. So what a lot of these vendors who make these FPGAs have done is they've engineered a DSP block, a digital signal processor block. And it's even faster than those lookup tables that I mentioned in the last slide. This is the inside. I don't really want to go too into it, but essentially the engineers have made these operations used for digital signal processing, which is typically multiply and accumulate functions. And they made it very, very efficient. So these can get done very fast, pretty much unlike anything else besides what hardware can do. Another one is block RAM. RAM just like in your computer, but it's much faster and much smaller. It's kind of like the SRAM, if you've ever heard of that. Usually much smaller capacity, but very fast. So it would place anything like a big memory that you want to synthesize and put it into a block RAM. So those are just some special blocks that FPGAs typically have on them, and the synthesizer can detect when you code something up that could use these. I know we're getting a little short on time here. I am getting to the end here, though. I just wanted to kind of go over, now that we're kind of done with all of the functional side of things, which I know might have been a handful, a headache maybe. But essentially, there are different FPGAs out there, and if you are someone who has had little to no experience or a lot of experience but is just yet to get a board of their own to play around with, there are some cheap boards. You know, FPGAs can range anywhere from thousands of dollars for industry uses, or maybe even just 50 to a couple $100 for something like an amateur at home design methodology. So a good starter board that I used was the Zybo, which is the one pictured there. I actually have it packed away in my closet somewhere. I used this on my senior design project at CSUN. I spent my own money to do it because I wanted to learn. And they have student discounts on the website. And the best part about this board is that it is an SoC. It's not just an FPGA. It has both the programmable hardware and it has a processor like a Raspberry Pi. and you can use them in tandem or separately. And you have all of those inputs like switches and buttons and LEDs and HDMI and audio in, and even some of these special ports here, which are PMODs. They're basically GPIO. So if you're looking to get into this technology, I'd highly recommend this board. If $150 is still too expensive, once again, FPGAs are more expensive than other alternatives, but there are cheaper FPGAs out there. They just may not be researched as much as the Zybo. There's a lot of tutorials out there like the Zinc book that can get you up and running with little to no experience. So that is something I would look into if any of you are looking to get started with FPGAs. It looks like I'm getting pretty close to time here, but essentially I was just going to go over my senior design project that I did last year, which was I used that Zybo on a project with Dr. Schall in the mechanical engineering department. And he needed something to be done with fast data acquisition. Essentially, we had a very high speed analog to digital converter trying to sample these ultrasonic signals, and they were trying to bring it over to a Raspberry Pi, which is not the fastest thing out there. It's small, but there's a reason it's small. It's not very fast. So what I did was I put a big middleman, which was the FPGA, and I had to code up these interfaces like SPI from scratch. And I was able to configure hardware to grab this data, buffer it out to the Raspberry Pi, and perform some digital signal processing on it in the middle. And it basically was able to take data from a chip that was very high speed data and take it, manipulate it, send it to a Raspberry Pi, and I was able to redraw those signals from a signal generator. So this is a very engineering specific project, but that's what FPGAs are great for. If you have a need that's very specific, you can code it up and make it very fast and efficient. So that was something that we did there. That kind of brings me to the end of my presentation, which actually looks good because we're right on time. But I did just want to say, coming out of college less than a year ago and now working into the industry, I'm sure just like every professor, someone has told you is that school is very different from the workplace. There's things that school doesn't teach you, specifically some of these few things that I've listed here. Learning Linux. Dr. Mailer, who just retired this semester, I believe, he came from industry, so he had us learn Linux. He only had us code up stuff on command line and text editors, no Vivado GUIs or anything, and there was scripting involved. And everyone was very new to this. No one knew what they were doing, but I appreciate the fact that he had us go through that tumultuous experience because this is what we use every day here at Raytheon. We rarely ever use any sort of GUI to help us out. It's all Linux command line. It's all scripting interfaces. So that's very important that if you want to work in this industry, that you learn and get comfortable with those. Another thing is to practice all the time. Obviously, we were in COVID. After I graduated, I had about 3 or 4 months of my time with no job. Applying for jobs was very hard. So instead, you use that frustration and put it into something. I did a lot of projects with my FPGA and my Raspberry Pi, and I learned new things. And I think it was actually thanks to that I was able to get a job with Raytheon. They saw that I was staying active, keeping my brain stimulated with engineering projects, and that I wasn't just doing it for the money. So if you were really passionate about engineering, you're going to find other things to do, in your free time. Even if COVID is happening, you're quarantined inside your house, just go on a website, just like FPGA for fun, look at projects, and learn something new. Never stop learning. That's another thing about being in the industry is learning doesn't stop at the end of college. I think I'm still going to be learning 30 years from now if I stay in this industry. So my last piece of advice for the industry is to become an expert with Microsoft Office, which may sound a little bit like a joke because every one of us here has had experience with it. Obviously, we all came from college and had to write essays or do a PowerPoint just like this one, but having to do the documentation side of engineering, which is something they're never going to teach you in school besides lab reports, which are not necessarily the most realistic bit. But, you know, for every design that we create, we have to create a very organized and thorough engineering report, multiple, like 10 documents per device or per module. And they have to have very specific page requirements and properties. So something I would recommend is becoming an expert, if not a master, at these things like Excel and Word documents and PowerPoint, because you're going to be using them almost every day. And a lot of the stuff I've actually had to learn as I go because I opened up some of their templates and I was like, wow, this is very neat and I don't know how to format this. So that would be my last piece of advice for any of you. And I am a couple minutes over, but this was my last slide. So if anyone has any questions about FPGAs or working in the industry or anything after school, feel free to ask me now. It's an open floor.
Can you go over the scripting languages you mentioned? Why would you use Perl and TCL, and what would they be used for? And why
So
those?
yeah, scripting languages, they're used a lot at my work. Essentially, they, in the Linux environment especially, they kind of bring together a lot of different functions. They can, it's basically a command line interface, but you're saving all of your commands into a file and telling it sequentially what to do. So, you know, in the FPGA world, if I needed it to synthesize and I needed it to simulate and place en route and verify, I can do that all in a scripting language. And then in my command line, I just type in one command, hit enter, and go eat some lunch for 20 minutes while it does its thing. And I don't have to sit there doing every single thing sequentially, separately. So a lot of these industries have created Perl or Tickle scripts, which, by the way, at TCL, they'll call Tickle sometimes. Essentially what they'll do is they'll have an engineer specifically write these scripts that are very generalized and that anyone can use, and it basically creates your job. It makes it a lot more efficient. So for instance, with Professor Mailer in ECE 527, that was Verilog for ASICs. We used Tickle a little bit. We had to learn as we went, but that helped us with a lot of the tasks that we had to do when we synthesized or that we simulated. So it's something that not a lot of people really look into until they need it. So that's why I would advise learning it now, because if you're going to have a job in this industry, I think it's unavoidable that you're going to run into some sort of scripting language. And you know, even if you learn one, you're going to know almost all of them. They're fairly similar. So
Okay, yeah, that's kind of what I was getting at. Did you mention those two in particular because they're only ones being used, or if you know of plenty other scripting languages, is that something that's probably good enough?
I would say Perl and Tickle are some of the most popular, but I'd say as long as you know a scripting language, once again, you know, if you know one software language like C or Java, you can usually become malleable and kind of transfer that to a different syntax. As long as you kind of get the gist of it and what scripting is, then I think you should be in a good place.
I have a question if you don't mind me asking.
Yeah.
What would be the best way to learn Linux? I've heard that many times that, you know, pretty much it's a big plus or even a must at this point to learn Linux for going into the
Mm-hmm.
industry. So I'm pretty unfamiliar with it and I have no knowledge on it at all. So what would you say would be like the best way to start, or like do you know of any resources that are like good for beginners?
Linux is kind of it's kind of interesting because it's kind of everywhere, but it's very behind the scenes. So, like you were saying, like you've heard of it, but you may not have dealt with it. And I was the same way. The first time I learned was with a Raspberry Pi. That's one of the cheapest and most efficient ways to get learning is because they use Linux, and it's also very user friendly. Essentially with the Raspberry Pi, you get a desktop interface just like Windows. Some Linux distributions don't even give you that. There's certain popular ones like Red Hat Enterprise, which are used in the industry. But the thing is, they're all based on Linux, which is essentially you have to be able to use the command line. With a Raspberry Pi, you get the best of both worlds. Most things on there have a GUI, but you can also get your command line on there. And you can, many websites you can Google or even just YouTube. You can just look at common commands of what's used in a command line. It's kind of daunting at first because you're just kind of used to being able to press a button and it works. But in Linux, everything has to be very spelled out. You can start maybe by just Googling basic Linux commands. There may even be some official support from the Linux team. It's open source, but they may have some documents on getting you up to speed. But there's things such as just navigating through the file system, which in the Windows world would be opening up File Explorer and going in and out of folders, copying, pasting, deleting. That would be like one of the first things I'd say to learn in Linux. Be able to, from the command line, create a text document, open text document, edit text document, save text document, change file folders. It's a lot of little things, and they're basic commands, and it would probably take like a half an hour, honestly, to learn those. It seems a lot harder than it really is, but just having any bit of experience with Linux such as that, I think is a plus, because I came into my job. Sometimes they expect people not to have any experience, but when they hear that you have, they think that's a big plus because it's a lot less to learn. You're already learning so much at a new job, so why have to learn Linux as well? But yeah, Raspberry Pi I think would be one of the first things because those boards are $25, $30. They have everything you need, and you can do a lot of cool things with them.
Thank you so much. I appreciate it.
Yeah.
You said you're still learning. Can you kind of go about what you're planning on learning for your future?
Yeah. I think engineering in general isn't just a topic that you go to school and you get your degree and you're done. With most STEM majors, you're going to be in the industry and you're developing things. You're doing things that no one has done before. So naturally, you're going to have to learn as you go and learn what works and what doesn't. But, going into, I guess, the more professional environment, it's also made me want to go back to school to keep learning. I'm learning on the job as I go, but then I realized going back to school would give me a lot better experience and in a much more friendlier environment. When you're in a work environment, there's deadlines and there's a lot of things that you can't dilly-dally on, whereas school is more of a more open interpretation and you do have deadlines for homework and whatnot, but you can ask a lot more questions. It's a supportive environment. Um, so I think once you even do get your bachelor's, you start working somewhere. You're either going to like working there and keep learning the workflow, the documentation, and you're going to change with the company as well because FPGAs are a fairly new technology. So things are going to change probably even in 5 years or less. And you're going to have to learn a new program or learn more about SOCs because those are popular. So, being in a technology industry is kind of tough if you just plan on going to school and making a bunch of money after that. Because if that's what you want, you're probably in the wrong profession, because you're going to be doing your job, smacking your head a lot on your keyboard when you spend 6 hours on something and you're like, I don't know how to do this. So you have to Google and keep researching until you find the solution, and then you learn from it. You take notes so it doesn't happen again. And eventually, when someone gets hired on below you and you've moved up, you can give them those notes and be like, here, I'm going to save you hours of headache because I learned all this and I'm going to pass it on to you. But I think learning is a very important thing in this industry. And yeah, it's not something that can be overlooked and just be like, degree completed, I can check out for the rest of my life.
If you don't mind, can we get into more detail on what you're trying to learn specifically at your job? For example, do you have like set goals you're setting yourself? Like, do you want to learn to get better at being a testing the program or designing it or documenting it? I'm assuming there's a lot of different engineers for one product. Is there like something that you're trying to focus on to specialize in?
Yes. In my industry, I mean, probably with a lot of these, you get moved around programs. So certain programs may deal with certain specific software tools or something of the sort. So specifically right now, my company uses Git, like GitHub. So one of my goals right now is to learn how to use Git from the Linux command line. I was a little bit familiar with uploading code and just doing a couple things throughout my school years. But now it's something that we use professionally, and you have to know all the ins and outs and all the tools it offers. So as you go through different programs, just like how I mentioned a few slides ago, I brought up all of these: Xilinx Vivado, Simplify, Libero, Model Sim, and Questa. As you move around programs, you're going to have to start changing what you know and kind of adapt to these different programs. In school, I learned Vivado, which was very easy, all-in-one GUI. Then industry, all of a sudden, level up, things get a little harder. Everything's from the command line. But if you're asking for, specific things, that specific programs or languages or something that I'm looking to use in my industry, I would say,
What do
obviously
you
you have
want
to
me to ask
learn
him?
VHDL. You would obviously have to learn VHDL or Verilog, Tickle or Perl, like I was saying earlier. Vivado would be a good starting place to learn a program, to how all of this works, from coding to placing and routing that whole design flow. And then eventually start looking into some of these other tools in the Linux environments. The only thing is, some of these tools are very expensive and licensed. So it would be pretty hard for an individual to get a hold of Simplify and learn how that works. But did that answer your question? I just want to make sure I'm understanding what you're asking. I'm answering what you want me to answer.
Yeah, I guess I was trying to get very specific in the sense of my assumption is, as a like HDL engineer, there's a lot of possible specializations you can get into. I'm not quite sure, as I'm not in that field, but I was curious if there's one field that you were trying to narrow in. Like, I'm not sure if there's difference between a verification engineer or a design engineer, test engineer.
I think there is. I'm specifically in development, so I deal a lot more with the VHDL design flow. Essentially, I create the circuits and I simulate them, and I try to verify that, and then it goes off to maybe someone from quality. Quality, I'm not sure on the specifics of their job, but they're probably very good at verification. They probably use some VHDL as well, but they would probably have to do a lot of scripting and maybe use a couple specific tools. Unfortunately, I wouldn't be very familiar with them, but I think in the world of hardware design, it really comes down more to the coding languages than anything, because like I was kind of mentioning before, if you want to go into FPGAs or anything to do with them, you have to know VHDL, And if you want to go into ASICs to develop anything from computer processors to even something for, kitchen appliances, you would have to probably know Verilog most likely. I'd say if you know one of those two or both, that would give you a good head start in hardware design. It's kind of tough to say since I haven't been on the other side as far as test engineers or verification engineers, but I would have to say even they would need to know that language. So that would be a good kicking off point.
Hey, Austin, this is Nick. How are you?
Good.
You kind of answered a lot of my questions. You were talking earlier about stuff. So I was just kind of wondering, since you work in design, so I guess you spend a lot of time just in front of the computer and creating the software and simulating it. But do you ever get to test it on an FPGA, on a product, on a board, or in the you ever get tested in the lab or anything like that?
Yeah. It's kind of tough. I joined this job during the peak of COVID, right after summer. But when I'm not working from home and I go to the site, I do get to go to labs. And we upload this code and we test it on the boards. We have all of that equipment in a lab, and it's not just sitting in front of the computer. I'd say most of the job is. However, when you need to go in and test something, you're the one to do it. You don't hand it off to somebody else usually. So, you get to do the exciting stuff. And specifically in my industry, I work at a pretty big company at Raytheon. They have a lot of resources. So, moving up from something from a CSUN lab to the resources that they have and what I get to work with, it's a pretty cool environment when I do get the chance to go to the site. So it's pretty exciting.
Yeah, sounds pretty cool. Also, so you do you work in VHDL, and also in C. You use C for the SDK.
Yes. Yes, we do use some C. Typically in the industry, my job title is considered a VHDL engineer. However, some jobs do bleed over into others. I believe Ian was the one who asked about, verification and test. When you're dealing with FPGAs, usually software kind of works in tandem with firmware, hardware. They're kind of analogous here, but I do have to write some C code to verify some of the code that I've done. So for example, maybe I wrote up a piece of hardware, uploaded it to the board, but typically in a lot of these large sized products in the industry, they're going to run in tandem with a software processor. So I need to write a piece of code for the software processor in C, because that's what most are written, or what most processors know. And I have to, tell it to interface with the hardware that I coded up and I uploaded. But it's usually very basic C. If, like I said earlier, almost everyone here has probably had some experience with a coding language. If you know one, you're gonna be just fine. The C that I've had to code has been very, very basic. It's just, reading a signal, reading what does this register have, or adding two numbers together. It's nothing too complex. It's not like linked lists or anything like that. But yeah, software does tend to bleed over into hardware, but usually it's not the other way around. Software developers usually don't know how the insides of the hardware works, whereas hardware engineers kind of get a little bit of both.
Sounds good. Thank you.
Question.
Yeah.
When you applied for your job, did they ever ask if you took the FE exam already?
No, actually. When I was looking for jobs, I was looking into that exam, just because I figured you know, since I don't have a job right now, I might as well work towards that. But they didn't actually. I do know within the company, though, they do have a lot of talk about engineering fellowship, where they look for FE and PE, the professional engineer exam, which comes after the FE. You know, they do have a lot of inside programs to kind of move you up if you're interested in engineering at that professional level. But it was never a requirement for them. I think just the bachelor's was the main thing. And the number two thing I would say is on your resume projects. Any sort of experience that you've had. It doesn't even have to be an internship. The reason that Raytheon got turned on to me actually was because of my senior design project. That was the first thing that they asked about in my interview, and they wanted to know more. They want to see more practicality rather than academic smarts, I think. You know, the FE would look great on a resume, but a lot of these companies want doers rather than the academia. So if they see that you've done a project and you've implemented in the real world a design, they're interested in that. They want to know more about it. So that's why I say if you're stuck at home during quarantine, if you're on a break from school or you're working less, you know, if rather than sit around or play games or watch TV, sometimes I'll try to pick up a project because that works me towards something. It's something that I enjoy too. So I think that would be a big piece of advice is, you know, you can go for the academia, but if you're looking for a job rather than to continue your schooling, I would say focus on a project and do something.
Okay, thank you.
Mm-hmm.
Hey Austin, I got a quick question.
Yeah.
I'm curious, like for every engineer or student rather, it's the question of a master's is always in place. I know Raytheon typically they'll pay your master's. They want in-house rather than kind of out of house. But what is VHDL or FPGA or Verilog type of engineer expect or want, or what does Raytheon desire in terms of higher education?
So like I said in the last question, you know, when I was hired on to Raytheon, it was bachelor's. You know, that's the first thing that they see. They do hire interns as well, pre-bachelor's, but you are correct also about the master's program. Companies like Raytheon or Northrop Grumman, they will hire you on, and you know, if you work for them long enough, or you know, some of them are even changing that, they will pay for your master's degree. For instance, I got hired onto Raytheon 4 months ago today, and I was able to sign up for a master's degree on their bill 2 months ago. I haven't started yet, but that's some of the perks of getting into a company. However, the drawbacks to that is you're going to be working full time as you go to school. So you're going to be very stressed out, but you're going to have a free education. Usually you have to sign up some contingency that you'll work for the company after you get your degree for so many years. But I think typically these companies will look for master's students, at least if you're coming straight out of school. You know, if you were somebody, say, you know, 30 or 40 years old with a lot of experience, they might look more at a master's or a PhD. But typically, if you're looking at jobs straight out of an undergraduate, I would recommend just applying for these companies, interviewing with them. Like I said earlier, if you have project experience and a bachelor's, that's the perfect duo. And they'll typically pay for your master's if you want to go back, rather than having, you know, a master's and no experience, because then you're kind of book smart but not street smart in a sense, without having any projects under your belt.
Thank you.
Yeah.
So if no one else has a question, I'm curious if you know a Raleigh Robertson at Raytheon by chance?
I do not. Unfortunately, it's a very big company, so only meet so many people.
What is it, like 55,000 employees?
It's large. My Tucson site is one of the biggest in the country, and I think that one alone is 13,000 employees, maybe 14. And yet it's a worldwide company, so. Anyone else have any last minute questions? I know we're getting on 7:30, but I'm open for more if anyone has any.
Check the chat, Austin.
The chat, let's see. Did not have that open. Do you have any media that we can follow up with you? What I can do, let me see which email. What I will do, let me see if I still remember my CSUN email. I'm gonna type my CSUN email into the chat. If you would like to ask me any more questions or have any advice or whatnot, you can contact me there. Let me just make sure I type it right here. I think that's something like that. It's been a while since I've used my CSUN email. I'll have to log in, but the first part is correct. The austin.smith.988, I believe.
I can verify that's correct.
Okay, cool. So yeah, if you have any more questions, you can email me there. I'll make sure to check it pretty soon here. And as I said earlier, I think Jason is recording this, and I can also send him the slides as well, because I know there was a few links on here. If anyone wants to leaf through these slides, they'll be available to you.
One last question.
Yeah.
Besides 520 and 526, is there a class that you would say was very helpful for you?
As far as FPGAs go, I mean, ECE 420 is the fundamentals of VHDL. 520 is the continuation of that, which goes into the tandem nature of software and hardware on the same device. 526, as I said before, I know Dr. Mailer recently stepped down and retired, but he was, I think he was my favorite teacher as far as learning digital hardware at CSUN. He was a very knowledgeable guy. I can't say from personal experience how the new professor is, but learning both Verilog and VHDL at the same time, really, I thought it would have been very daunting at first because it's having to learn two different languages on the same thing at the same time, but it actually helped solidify basically the nature of hardware, because it's not just the syntax. You have to understand the behavior of hardware versus software. So I'd say ECE 420 and 520 are good. ECE 526, which was the intro to Verilog. ECE 527 was a great class as well, but I'm not sure if it's offered currently since Dr. Mailer stepped down.
It's canceled this semester.
Yeah, so if they do offer that, that was one of the hardest classes, but I thought it was a very knowledgeable class, especially if you're looking more specifically into ASICs. I have not taken Mirzai's 524 class, but that is also a continuation in FPGAs from ECE 420. So I'm sure that would be a good class to take as well. Mirzai is very good at interacting with the students. I felt like Mailer was very knowledgeable from industry, but Mirzai is a very good teacher. He's able to kind of word things in a way that's easier to understand. But I'd say those 5 classes would be the best if they're offered. So just to reiterate again, ECE 420, ECE 520, ECE 524, ECE 526, and ECE 527.
I have a question.
Yeah.
Yeah, so you said that you are gonna get your master's degree?
Yes, that's correct.
Yeah, I was wondering if you're doing that for your own good or you're doing that for your like career wise in the field. Like, is it gonna help you bump up the pay or knowledge wise?
My master's was something I was looking into actually before I got hired on. Basically, I set a goal for myself that said if I can't find a job during COVID, I'm going to go back to school because I don't want to just sit here. I want to keep learning and, bettering my knowledge. But once I became hired by Raytheon, I knew about their program. So obviously there was more of an incentive because it's free knowledge, and there is, I believe, a pay bump. Just because you have a master's degree. I'm not sure what magnitude that pay bump would be, but by the time you finished your master's, you probably already have gotten a promotion from say an engineer 1 to an engineer 2. So that's there, but I think it's also important that you do have the personal drive to go back and learn, because like I said, if you're in engineering just for the paycheck, I think you're in the wrong job. It's something that needs to be studied and have a passion for. It doesn't have to be your entire life. You can have other hobbies, but going back to school was something that I personally did want to do. Not just because of the pay bump, even though it's a nice perk.
Yeah, okay, that makes sense.
Mm-hmm. Anyone else? Final call? All right. Well, I think that is it then. So I just want to thank you all again for coming. I know it might have been a lot of information, but I hope it was useful to you all. And like I said, if any of you have any more questions, my CSUN email is in the chat. You can get a hold of me there. And Jason is recording this event, and he will have the slides from this event that he can send out to you guys at your request. So
thank you so much for doing this.
Yeah, not a problem. I enjoy it. So thank you all for coming. And I guess I'll turn it over to Jason if he has any closing words.